Hello everyone, welcome back to the channel. If you have ever worked with databases, built a data pipeline, or tried to tune a slow query, you have probably run into a fundamental question. Why do different databases store data differently? Why is it that the SQL Server or PostgreSQL database running your application feels blazingly fast for user logins, but completely crawls when you try to run an annual sales report? And why do modern cloud data platforms like Snowflake or lakehouses like Databricks use entirely different file formats like Parquet? My name is Durga Prasad Patsa and I'm a data architect. And in this video, we are going to break down the massive architectural divide between row storage and column storage. We will look at OLTP versus OLAP, online transaction processing versus online analytical processing. And by end of this video, you will exactly understand why modern data lakes are built the way they are. Let's dive in. So before we look under the hood, let's address the elephant in the room. Why can't one single storage format just do everything well? As a data professional, or one of the first things you learn is that a single system can rarely optimize for two completely opposing workloads. Look at the architecture diagram. On one side, you have applications. Think of a bank app or an e-commerce checkout cart. They need fast individual transactions. They care about one user at a time, inserting a balance, updating a password, or deleting an item from a shopping cart. On the other side, you have analytics. This is your business intelligence, your AI models, your executive dashboards. Analytics doesn't care about one specific user. It cares about aggregates. It asks questions like, what was our total revenue across the 5 million customers last quarter? One storage design simply cannot optimize both workloads efficiently. To see why, let's use a simple analogy. Imagine you're designing a physical library to store customer data, and you decide that every single customer gets their own dedicated book. Inside book 101, you write down everything about that customer, their name, age, city, salary, and phone number. Book 102 gets exact same layout for the next customer. Because everything about one customer is bound together in a single book. This layout is incredibly efficient. If a customer walks into your library and says, "Hey, I need to update my phone number," you grab their book, flip it open, change the number, and snap it shut. In the database world, this is exactly how row storage works. On the physical disk, all attributes of a single row are stored sequentially, right next to each other. But now, let's say the CEO of your company walks into the library and asks a completely different question. What is the average salary of all our customers? If you keep the library organized the old way, you have to walk down every single aisle, pull down every single book, flip to the salary page, write it down, put the book back, and move to the next one. If you have millions of customers, you will be exhausted before you even get halfway. So you decide to rearrange the library entirely. Instead of organizing by customer, you organize by attribute. You dedicate shelf 1 exclusively to names, shelf 2 stores only salaries, and shelf 3 stores only cities. Now, when the CEO asks for the average salary, you don't touch shelf 1 or shelf 3 at all. You walk straight to shelf 2, scan it from left to right in one continuous motion, and calculate the answer. This is the core philosophy behind column storage. Each shelf contains exactly one attribute. Let's translate this from library shelves to actual physical disk layouts. Look at the data on your screen. It's the exact same data set, but look at how differently it is organized on the hardware level. On the left, row storage writes customer 101's entire record, then immediately writes customer 102's entire record right next to it. On the right, column storage groups all the IDs together, then all the names together, then all the cities, and then all the salaries. It is the exact same data, but different organization. And this organizational shift changes everything when it comes to computing performance. This brings us to OLTP, Online Transaction Processing. These are your operational databases like SQL Server, Oracle, PostgreSQL, and MySQL. When you swipe your card at an ATM, modify a mobile banking setting, or add items to an online shopping cart, the system needs to execute what we call point queries or single window mutations. Because row storage keeps the entire row together, the database can locate and read that specific row on the disk instantly. It gives you blazing fast inserts because it just appends a new book to the end of the shelf. It gives you fast updates and deletes because it modifies data in one single physical location. If your application's primary job is handling thousands of split second individual transactions per second, row storage is king. But what happens when you move over to the analytical side of the house? Welcome to OLAP, Online Analytical Processing. When a data analyst, a data scientist, or a business intelligence tool runs a report, they are looking for trends. They want to know monthly sale trends, top performing products, or average revenue. Out of a production table that might have 100 columns, they usually only need 3 columns, such as sales, date, and product. If you used a row-oriented database for this, the system would suffer from massive unnecessary disk I/O operations. It would have to read all 100 columns off the disk into memory just to throw 97 of them away. With column storage, used by powerhouses like Databricks, Snowflake, Microsoft Fabric, and Google BigQuery, Amazon Redshift, the engine bypasses the other 97 columns entirely. It reads only the specific columns requested. Now, let's look at this slide because I want to give you the actual engineering secret sauce behind why columnar storage achieves these insane speeds. It boils down to two core concepts that you will absolutely be asked about in system design interviews: run length encoding and column pruning. First, look at the 10 times higher compression metric. When you store data by columns, similar values sit right next to each other. Imagine a column for country where you have USA repeated 5,000 times sequentially. Instead of writing USA 5,000 times to disk, the compression engine uses run length encoding (RLE). That single optimization collapses your storage footprint, giving you up to 10 times higher compression ratios compared to traditional row-based layouts. Second, let's look at that 90% less disk I/O. Because the data is stored in isolated columnar blocks, query engines use a technique called column pruning. If your query only asks for salary, the engine entirely skips the blocks for name, city. By skipping entire blocks of unnecessary data and reading highly compressed streams, you cut your disk I/O drastically. That is why an analytical query that takes minutes on a traditional row database finishes in seconds on a columnar platforms. Now let's tie this to the modern data architecture you see in the industry today. You have likely heard of data lakes, delta lake, or lake houses by now. In a typical modern data pipeline, data is extracted from application databases via ETL or ELT. ETL is extract, transform, loading, and ELT is extract, loading, and transform processes. But we don't store it in raw text or raw formats in our object storage. Instead, we land it into open source columnar file formats like Apache Parquet. Why? Because formats like Parquet bring the power of column storage directly to cheap cloud object storage. By structuring data columnarly inside Delta Lake, Apache Iceberg, or open formats, we get the best of both worlds. We can store petabytes of data cheaply, compress it to a fraction of its size, and allow Power BI or Tableau or machine learning model to scan billions of rows in seconds. We read only the required columns, store data once, and analyze it at absolute scale. To summarize everything we talked about, let's look at this definitive comparison matrix. This is the takeaway of this is the takeaway you will want to remember for your design docs or in your next technical interview. Row storage is built for OLTP. It is bread and butter, is handling fast individual transactions by reading and writing entire rows at a time. It is optimized for fast updates, which is why it powers engines like SQL Server, Oracle, and PostgreSQL. Column storage is custom built for OLAP and modern data lakes. It is designed for heavy analytics, reading only the specific columns you request. It shines at fast aggregations like sum, counts, and averages, and powers platforms like Databricks, Snowflake, and Fabric. Neither is better than the other. They are just engineered to solve entirely different problems. So at the end of the day, if you understand the core differences between row storage and column storage, you have already mastered one of the most fundamental architectural divides between traditional databases and modern cloud data lakehouses. The next time you choose a storage format or write an optimized query, think about how those files are sitting on the physical disk. If you found this breakdown helpful, do me a huge favor. Hit that like button and subscribe to the channel for more data architecture deep dives. And drop a comment below letting me know what architectural topic you want me to cover next. I am gonna cover uh, a most important topic, which is LTAP, lake-based transactional and analytical processing, which is the Databricks' recent invention of combining both OLTP and OLAP into one single engine. Thank you so much for watching. I'm Durga Prasad Patsa, and I'll see you in my next video.